Welcome to the next edition of the InfoQ podcast. My name is Wesley Reisz, and today I'm talking with Slava Oks. Slava has worked for Microsoft for almost 20 years, working on a number of flagship products, including SQL Server. He also led the kernel team for the Midori operating system, and more recently worked actively to bring SQL Server to Linux. This podcast focuses on a lot about that project and exactly how he achieved it. So welcome, Slava, to the InfoQ podcast.
Yeah, happy to be here. Thank you.
I appreciate you taking the time to chat with us. So how in the world did you get involved with a project to take SQL Server, which is, I don't know how many millions of lines of code, but to port that off to Linux? That sounds like a daunting thing to try to get involved with.
Yes, I can't agree more. So in 2000, beginning, actually exactly 2 years ago, that's actually an interesting point. Exactly 2 years ago, I started working on this project. Before that, I was looking for something interesting, and my former colleagues from SQL Server team, they approached me, and they kind of say, hey, we're considering putting SQL Server on Linux. So I thought about it, and of course it's a daunting task, and I initially didn't want to take it, but then after realizing how we can make it happen, I decided to jump on it, and here we are.
Yeah, and how you started to implement it was pretty cool. It kind of tied back from Midori to some things that you did with Drawbridge. Can you talk a bit about how you were able to actually port?
Yeah, yes, of course. Yes, and without the approach that we actually taken, it would be like tremendous task for us.
Yeah.
So when I heard about it, and I was talking, as I actually mentioned a little bit in my blog, I was talking to my friends, and I said, look, I wish we had a Drawbridge. Something popped up out of me, like we had the Drawbridge, because in my previous project, I worked on an operating system called Midori. That was the experimental operating system that we worked for some time, and I led the kernel team there, and I was involved with Drawbridge. And the idea was there to, as Midori and Drawbridge, we had customers that wanted to have a back compat story, and they wanted to run some Windows applications in Midori. So we brought Drawbridge as a platform abstraction layer to do so. And so, and due to the Midori nature, it had taken us like less than 6 months to do so. So I had that experience, and my team had the experience. So when I was tasked with and started thinking about Linux, I thought, hey, I told my friends if we had a Drawbridge, then the task would have been easy, and laughed to myself. But then the more I thought about it, the more the thing became real. So I thought about it. I talked to a few folks, engineering folks that were involved on the kernel team, Midori kernel, former Midori kernel team, some MSR folks, and we got lucky because there was already prototype of SQL Server running on, not SQL Server, sorry, of Drawbridge running on Linux. And so I actually taken that prototype, and we take it and we start pushing it forward. So that's kind of.
And it just worked perfectly right out of the bat, right?
Oh, I know, of course not. Not perfectly. So I took the guys actually did some work. They were able to bring up some a Windows application on Drawbridge and Linux, but at that time you could not debug. It would crash, and it would crash and burn pretty much every other time. So I took SQL Server bits and put on it. I had to fix some bugs here and there, but fixing the bugs were like tremendous. Like it was very hard because you don't have any exposure what's happening inside. So you had to actually pretty much guess, and printfs would not help. So it was quite a bit of fun journey.
Yeah.
So after I boot up SQL, it did work. I could get it like at that version, select one, but then it would hang every other time. So as well, so it wasn't as easy as it sounds.
Okay, Slava, let's back up for just a minute. So you mentioned Drawbridge a little earlier. What exactly is Drawbridge? What's the purpose of it?
Yes. So the Drawbridge was a project that came out from Microsoft Research, and its prime focus was to introduce security and high density containers, I would say, into the cloud world. And so the idea is that you take user mode kernel, and so they took actually Windows kernel and they put it in user mode by cutting out the pieces that rely on ring 0, and then you would have that kernel that would boot unmodified Win32 binaries, runtime, and then the binaries. And then this way you will be able to provide the density and security at the same time. And so that's what the idea of the Drawbridge. But then that was the initial idea, and that's what people were trying to productize. But then over time, in some cases, people start using it as a research project, or like we use it on Midori as a platform abstraction layer. So I know we used it in Midori, and then there was another attempt for operating system called Battlefish. There was an implementation there, and then of course there was a Linux prototype as well.
So you talk about a couple words there that jumped out at me: density and security. So density meaning you're running multiple applications in the space.
Yes. So, like, as you know, in the cloud, the cogs are matter, right? So you can try to save every bit byte and CPU cycle. Generally speaking, like VMs, they are slimming down, but it takes a lot of time and it's lots of effort from an engineering effort from both kernel team and hypervisor team. So, like as a business, we're looking for the density solution in the midterm before VMs will become viable to actually pack more applications into the given on a given hardware.
Right.
And so the Drawbridge was an effort to do so. The Drawbridge technology, basically, is to be able to run more applications with a given hardware without consuming much resources.
Now, the Drawbridge also takes I guess a number operations that are being pushed to the OS and reduces it down to a subset, like somewhere around 50, right? I think it's called ABIs.
Yes.
What's an ABI?
So ABI is the application binary interface, and this is what one of the key parts of the Drawbridge research was to show that you could run around any runtime or kernel runtime in user mode, basically just providing 50 ABIs, limited number of calls, without, like, in general, operating system exposes about, let's say, depending on type of the operating system, X number of 1,000, up to 1,000, 2,000 number of system calls, or you can say the ABIs also. But to implement all of this, it's going to be tremendous amount of work. And so what researchers show that, hey, you can actually take just 50 of those guys and implement a kind of trim down the rest of the 2,000 down to this 50, depending on the requirements and depending on the functionality that you want to enable. And so that's where also security comes into the picture, because now instead of securing 2,000 or 2,100 syscalls, you need to make sure that your 50 calls are secure, and so it's pretty much amount of things that you need to worry about is way less, and that's where the security play was coming from for Drawbridge.
Right. So when I see some of the diagrams, I see Drawbridge and then I see security. Mm-hmm. How is security managed? Is there some separate module that passes through to?
That's correct. So on Windows, when the Drawbridge consisted of three major pieces, right? One is called LibOS, it's library operating system, which is in user mode kernel. That's the first piece. The second piece is a driver, which is the driver, like saying something, and I believe they refer this to as a PAL, platform abstraction layer, and that driver actually implements these 50 ABIs. So what it happens is that you run in user mode, but then when you need to make a call into the kernel, the only way you can call into kernel by supplying one of these 50 syscalls. That's about it. If you try to call anything outside of the range or outside of the table, a driver will take the entire subsystem down. And then there was a third component, which is called DKMon, Drawbridge Monitor, that was actually responsible for doing managing the resources and providing the security validation, so authorization, I should say. So when a file application that runs on top of Drawbridge wants to access resources on a host, like the file system or network, and need to echo something, that all goes through the security monitor.
Wow.
That's DKMon. That actually does, let's say I want to open a file on a file system. I'm echoing that file on the file system through DKMon, I open the handle, and then I take that handle and insert it in the Drawbridge process, in Drawbridge, and now Drawbridge can use that handle. So that's where the security came from.
Got it. Okay. Yeah, makes sense. All right. So I want to ask you another question. Earlier, you mentioned libOS. Now, libOS is a slimmed down version of Win32 kernel. Is that right?
So libOS consists of two major pieces. The first piece is the upper part is implements NT user mode.
Yep.
So what it pretty much implements those like NT user mode. NT today, let's say, implements 2300 syscalls, syscall. So NT user mode is exports these syscalls, so that NT-DLL and other DLLs and applications can call directly into the into user mode. That's the first part. The second part is a Drawbridge runtime library, which actually supports this NT-UM. So NT-UM, into user mode, is basically provides the calls and semantic of the windows that applications rely on, and then there is a runtime that implements those semantics, that helps to implement those semantics.
Got you.
And so that's what the libOS. And the NT user mode is pretty much modified NT-OS kernel that has scheduling and ring zero functionality cut out, like page table management, like interrupt management, and so forth and so forth.
So what does the whole stack look like when you're running this on Linux? You've got some kind of launcher, something that's running.
Yes. So let's transition to briefly to Linux, because architecture on Linux is different slightly than architecture on Windows. Because on the Windows it was security and density play, where on Linux it's more platform abstraction layer.
Okay.
And so on Linux there is no driver. The bottom part, which driver was on Windows, and actually combination of the that special process that I talked about, the kmon process, and the driver is put together into one place, and it's implements at the bottom of the process of the Linux process. So when we launch SQL Server on Linux, the first part that starts is our Linux binary, which is combination of what was on Windows as a driver and that special process. And so we pretty much we open the package, the first package that we need to open, and then we set up the call table that we need to provide to upper layer, to the Drawbridge layer of libOS. We create that call table, and then we create a thread. We load the initial binary, which is what we call SQL PAL. So I want to also forgot to do this transition where on Linux we now, instead of calling all these binaries and everything Drawbridge and libOS, we actually came out we're using it as a SQL platform abstraction layer, which consists of what was formerly was libOS and SOS. We can talk about what SOS is, but basically SOS is what in Drawbridge was the RTL, Drawbridge runtime library, and the rest of the SQL PAL is pretty much is libOS, what it used to be. So when we start the process, as I said, we initialize all the runtime, memory, whatever, like the bottom part of the memory, whatever we need to run the Linux version of the code, and then we load our binary into the memory, and then from the package, that's a SQL PAL binary, and then we create a thread, and that thread enters that binary, right? And from that point on, we're already running in. It all happens within the same process space. It's just we transition into the PE binary, which now start initialization of the SQL PAL itself. And so in terms of the architecture, if you think about it, there's at the bottom, there's what we call host extension. Then there is a SQL PAL. And then on top of SQL PAL, as I said, consists of into user mode and libOS and SOSv2. And then on top of this, we have Win32 runtime, which is NT-DLL, which is kernel 32, all the runtime libraries that we need. And then we have a SQL Server process itself running on top of it. Now, from the SQL PAL, we now not only exposing exports that required for Win32 applications, as we said, talked about syscalls, but in addition, we are also exposing SOS APIs, which SQL Server relies on. So SQL Server can call directly into the SQL PAL by passing Win32 runtime libraries.
SOS is the SQL operating system, is that right?
That's correct.
Refresh my memory. That was, if I remember right, it was some things that gave you insight into the OS from SQL Server.
Yeah, so SQL OS was put together for Yukon 2005 SQL Server version. It's a combination of operating system services like memory management, scheduling, synchronization primitives, and I/O. It's not a platform abstraction layer, but it enables developers inside of the SQL Server to take advantage of the operating system and not to worry about where the memory comes from, how to schedule things, where to use threads, how to use threads. So they don't have to worry about it. Everything happens for them automatically. So it's a runtime library that provides operating system services.
So now that's inside of SQL PAL?
So now, yes. So we had a dilemma when we started working on productizing Drawbridge and all of these binaries. So we have two major pieces, right? We have a LibOS, and that's an end-user mode that exposes end-user mode semantics, and also the Drawbridge runtime library. And then we also have SOS, which is inside of the SQL Server. So if you look at the entire stack, you'll see lots of redundancy. One thing. And the second thing is that DRTL, the Drawbridge runtime library, was not implemented in such a way for high scalable, high performant applications like SQL Server, right? So it was pretty much, it served its own purposes for the apps that it was built for, but there is no way we could run SQL Server on top of it. So what we had to do, we had to take DRTL and evolve it into highly scalable, highly performant, debuggable, supportable layer that we already had in SQL Server. So instead of reinventing the wheel, we made a decision. Actually, in fact, we made a decision December, not last year, the year before, end of 2015. I spent some time sitting in the office while most of the folks were out, actually going and analyzing, trying to figure out how to approach the problem. And so we had a few proposals, and also one of the proposals was actually taking SOS and put it recompiled natively for Linux. But then we decided that it doesn't make sense because we want to use the same code and the same kind of features everywhere, both on Windows and Linux. So putting it inside of the SQL file and in one common place totally made sense.
Yeah,
that's what we did. So we start moving SQL OS from SQL Server and removing the Drawbridge runtime library.
But now, if I remember right, there were all kinds of things that you could do with it, right? There were things like through transact SQL that developers could interrogate. Is all that still available with this approach?
Of course, that was another thing, right? So so I was involved architecting and building SOS to begin with, and we worked with supporting and maintaining database engine, and at scale, it's an enormous task, right? And so we worked very closely with our support team, support engineers, to actually make the product supportable in such a way that you don't need to attach debugger. So if the issues come up on the customer side, that they're easily diagnosable. So we created this notion of DMVs, dynamic management views, and we exposed all state of the SQL Server or SOS through T-SQL language. So if you're a DBA or you're familiar with T-SQL, you can understand what's happening in SQL Server in terms of runtime. And that was another reason why we decided if we move it down from SQL Server standpoint of view, everything is going to come together and you will be exposing even more information than before.
Okay, so effectively you're taking the Windows binaries, wrapping them, and then running them directly on the Linux binaries, and you're pretty much running the original code, right?
Yeah, so the instructions are instructions. So we run on Linux, we run everything in user mode. It's still Intel architecture. So all we need to do is to pass the control from one world, I would say, to another world, right? So when we run on Linux, the binary formats are different. So the native Linux loader needs to be aware of L format, and that's what it uses to load Linux binary. Once the binary starts and up and running, then we use our loader, which is inside of that process, to load our binaries, which are PE binaries. And once we load them, we can say, hey, CPU, we can transition the execution through the function pointer into that binary, and the code will start executing.
Nice.
So the only time when we need to worry about is when, while we're executing in PE world, we want to go and make a ABI call into the ELF. So we need to create some calling convention that we need to follow. And so we implement in some assembly stubs that we actually do that.
Very cool. So there's two things I want to ask about. One is you've been talking about kind of user mode and multiple users that's there. I'm curious about how the addressing space works from the Windows world all the way down to Linux, how that happens.
Yeah.
And then I'm also curious about, and this will tie back to your talk in QCon London, where you're talking about the performance of the stack, because I'm really curious how performant the entire stack is. Let's start off with the addressing question. How do you manage the addressing space between Windows and Linux?
Yeah, so that's one of the key problems that we had to solve, because the last thing we want is one world to stumble on top of another world, right?
Yeah.
So what we're doing, one of the keys that we follow is the design principle is that if the code can live inside of SQL file, it has to live in a SQL file.
Okay.
Means that once we started the process, once we did all the initialization inside of host extension, inside of Linux portion of the code, once we've finished that, we should not be doing any memory allocations inside there on behalf of SQL file. So that means that just to minimize the possibility of one world stumbling on top of another world. So that's a design principle that we follow. But now, once the Linux world started, what we do, we actually carve the big chunk of the address space for the Windows. And so when we launch SQL file, we have this special page where we pass the information about the configuration, about the layout of the address space, and so forth and so forth. And so, like, we pass the same way NUMA information, we pass the same like CPU information, and we use it as a communication channel as a bootstrap channel to launch SQL file. So when SQL file launches, it looks at what is the address space it can use, and it takes this gigantic address region, and then it has its own virtual address space manager to actually manage the space. So when Win32 world starts, it says, hey, I need to do virtual alloc of this address space. SQL file implements actually virtual address space manager that carves these regions of the address space and gives it to consumers. And then consumers use the address space manager APIs to commit it, which address space manager then goes and turns them into map calls, Linux calls to map that memory.
It's secure. You don't have these things stepping on each other.
So it's best effort guarantees, right? I mean, of course, it's not secure. They're all running within the same process space. So if we accidentally load a binary that has a memory corruption, you could easily corrupt either world. But we try to keep them separately, so they live into different regions of the address space. So this way we have so if we manage them correctly, we minimize the possibility of memory corruptions coming from one world to another. Because sometimes it's like the problem, memory corruption problem is hard when it's in your world, but when it's cross worlds, it's going to be even worse.
Yeah, I can imagine.
So we're also using a bunch of debugging tools on Linux to make sure like it escapes me the name right now, but it's to make sure that we don't stumble on each other by running under those tools and like randomizing memory allocations and putting a bunch of debugging in places so that if there's a memory corruption somewhere comes, we can catch it easily. Yeah. It's Valgrind. We got the tool that we use in the lab to make sure that run kosher.
So, all right, let's talk about performance then. So you're taking 1,200 Windows calls, reducing them down to 45 or less of these ABI calls. How performant is this? Is it going to measure up to the performance that you get from SQL Server on a Windows environment?
Yes. So If we didn't believe this, we would not start the project, because performance and scalability is one of the key features of database engine or sophisticated SQL Server.
Sure, of course.
So I personally strongly believe that we can pull it off. But the problem we face in ways is that you have a multi-layer redundancy, where SQL Server has SOS runs on top of the into-UM runs on top of DRTL, and DRTL runs on top of host extension, and that runs on top of Linux kernel, and that runs on top of hypervisor. Yeah. So you get like 5-6 layers of redundancy doing the same thing again and again and again. But because I knew how SQL Server works, I knew how Drawbridge works, and I knew how it has to be provided from host extension. I realized that we can actually do lots of optimizations around that. So when we're preparing for CTP 1.0, which we released in November, we actually started lots of performance work. We haven't started. We started a little while back, but we actually did some of the key parts of the performance work. And interestingly enough, that work was less about smashing the layers. It was more about removing inefficiencies inside of the DRTL, because we haven't had SOS at that point in the picture, and we're still working on bringing SOS, so it's quite a bit of engineering work. So there is, like as I mentioned before, Drawbridge was built and LibOS was built for non-high performance, high scalability applications. It filled its niche. That's about it. So there was lots of global state. There was lots of contention around the global state, and then there was also code path lengths issues inside of the LibOS, like going from entering inside of the LibOS, going all the way down to the driver. There was a huge number of instructions that we could remove. Yeah. So we looked in there. For example, I'll give you an example. So now we have our own virtual address space manager. In the Drawbridge actually relied on Windows to do address space management, because it's pretty much the same thing. So it would not have its own virtual address space manager inside of the DRTL or LibOS. It will call into Windows kernel to allocate address space, address region, and then commit or decommit it. Then once the page was coming back, in order to make sure that things work properly and so forth, and they're trackable, they had a global state for every address region. So that means that it's either any allocation coming from any thread or from any process within Drawbridge that runs inside of the same Pico process or Pico address space, it will acquire global lock. So for us, like even on the startup time would take forever, because especially if you think about high-end terabyte machines, contending on that global lock for every virtual alloc would be a humongous problem. So what we had to do, we had to eliminate that global lock. So that's where the new virtual address space manager came into picture. The other example is that the entire LibOS was built on the single heap. And again, it was a huge contention point, because every allocation, dynamic allocation that was coming from, let's say, on IO pass, when we issue an IO, for SQL Server issues an IO or the other component, we have to allocate IO request, and that IO request was allocated from global heap, which was protected by global lock. And so then when you try to scale that thing, and SQL Server runs lots of threads and lots of issues, lots of IOs, you hit the bottleneck. So we had to remove that bottleneck. Also, we had to optimize for CTP 1.0. We had to do lots of work around optimizing code path lengths by eliminating lots of memory allocations, period. You just look at the code and you realize that you can cut off a bunch of memory allocations. And so we did that work, and that A, eliminated contention, and then B, it minimized the code path lengths for the execution. So that brought us actually within for core benchmarks. I cannot say on a high-end hardware, but on a two-socket machine, let's say those were 16 ways, 16 logical processors with 64 gigs, 128 gigs of RAM. That brought us within 20% of Windows, comparable benchmarking, the workloads that we run. At that point, we hadn't done the major work that I talked about from SQL Server calling directly into the Linux world. So after that, we actually been focusing on optimizing the code path from SQL Server calling into the host extension directly. So, in fact, I just sent the code review today where I'm taking as we enter into to generate disk.io calls, like I say disk.io, I just directly, I do some checks, and I can actually call directly into the Linux world, right at the entry point. And with this change, I eliminate about at least 1,000, maybe to 2,000. I don't want to give you the measure in terms of instruction count, but significant number of instruction gets eliminated. And on some of the customer workloads that we're seeing right now, it's this only change brings us 20% improvements.
Awesome.
And this is not talking about network I/O. And in network I/O, we have a bigger fish to catch, actually. There we have lots of inefficiency that we're working through right now. And once we're done, I mean, like, it's going to be beautiful.
That's amazing. Thank you so much, Slava, for taking the time to join us. We've been talking with Slava Oks of the SQL Server team that ported the platform to Linux. I'm very much looking forward to hearing this talk at KubeCon London, so I hope you can join us this March.